So we're going to keep the ocean thing going here with Christopher Wolfe.
Okay, well, so I've been away in Liverpool for the past year, so I missed the first two of these. And so when Brian came and asked, could you give a 10-minute presentation on the stuff you do? I think I misunderstood. Instead of on a thing that you do, I thought you meant on all the things that I do. So I thought, well, 10 minutes isn't very long, but I'll try. So I'm not gonna.
It's 10 minutes, so.
Yeah. Well, so there's various interpretations of what we do with this. But so there's some slides that have a lot of things on them. Anyway, but I'll just focus on some of the highlights. So since I have been gone, there's some people here who've never seen me before. So I'm a physical oceanographer, and I do sometimes dabble in climate dynamics, and I'm a known chop enthusiast. And so some of the things that I do, the main thing that sort of binds them together mostly is theory and idealized modeling. When people think of modelers, they often think of people that are trying to get this current to be exactly like the current in reality, and that's not what I usually do. So I'm just going to hit on a couple of these points in a little bit greater detail. So this is sort of what I started out doing, is looking at the overturning circulation of the ocean. And it is something that I'm coming back to. I'm working on a project with Kamazima about this, where we're trying to do it in a much more realistic setting. But for those who don't know, the overturning circulation is this global ocean circulation where you have water that is formed at high latitudes, and it sinks and flows throughout the globe, and sort of fills the ocean basins below about 2,000 meters, and then it upwells again, and it turns out to play a large role in regulating climate and life. And the way that I approached understanding this, I basically want to just understand, how it works. Like, if you change this real basic thing, how does the overturning circulation change? And so my animations have stopped, and so the approach that I take are using these very idealized models. So this would be my idea of what the ocean looks like. It's a shoebox, essentially. And the main things that it has in common with the ocean that we know is that it's got height, width, and depth, and coasts, and a part where they're in two hemispheres, and a part where the water can go around, sort of like Antarctica. And the question that I was trying to answer here was, how do you connect the effect of this large scale overturning circulation that involves the entire globe with the most energetic parts of the ocean circulation, which are mesoscale eddies, which are things that have about a 100-kilometer length scale and a couple of week time scale. And so to answer that with a full-blown global model would have been hard. This is why I focused on a very simple model. And we were able to show that, in fact, that the eddies are essential for setting the stratification of the Southern Ocean, which then determines how deep the stratification is and the strength of the ocean. But then once you have this sort of setup, you can look at a bunch of other topics. And so something that is of interest in the real world is this concept of multiple equilibria and hysteresis in the overturning circulation. And the idea here is that what this is showing is some measure of the strength of the overturning circulation. And this is showing how much fresh water we're adding to the northern hemisphere. So you can imagine, in reality, what you're doing is melting Greenland, say. And what happens is, as you increase the amount of fresh water you're adding to the North Atlantic, your overturning decreases, and then at some point it reaches a critical threshold, collapses, and then you can keep increasing the amount of fresh water you put in the North Atlantic and keep going back. But then let's say we fix the problem and we stop adding fresh water to the North Atlantic, and you start coming back and decreasing the amount of fresh water you're adding. you find that you pass the place where you had a collapse, and you have to keep going back further and further and further. There are two, this is called bistable systems. There are two regions where you can coexist with the same amount of forcing, and you end up in this off state for a long time until you pass another critical threshold and go back into the on state. And so I looked at this in terms of dynamic system theory and orbits of orbits in phase space. And this is a sort of question that we're coming back to with Kamazima, where we want to do this in the more realistic setting. And instead of this very simple dynamical systems approach, what we're going to do is try and look at various ways that people infer the strength of the overturning circulation in the modern world, and use machine learning to try and understand if those things are reliable. Because people have, if you've been paying attention to, say, the New York Times or the Washington Post, there's occasionally these articles about, oh, well, we use this proxy to infer the strength of the overturning circulation, and it's going to collapse tomorrow. And then someone else comes along and says, well, I have a different proxy and it's not going to collapse tomorrow. And so we want to sort of unravel that using machine learning. And skip ahead to, so I'll just say I do mesoscale eddies and mixing. I do some observations. I don't actually go out and observe them. So these are like satellite observations and hydrography, but I have spent a bunch of time trying to understand the variability of the Gulf Stream, which is a real current that really does things. And the sort of the question that I was trying to answer was, is the Gulf Stream migrating or slowing down in response to climate change? Because there are a lot of forecasts of the future state of the Gulf Stream that suggest that it will slow down. But the people are like, well, if you look at it this way, it's been slowing down. And so we decided to look at it really directly by just looking directly at the latitude, speed, and transport and width of the Gulf Stream using satellite altimetry over the past 30 years to see if we could actually detect a trend. And what we found was that any trends that you did find were small compared to the interannual and decadal variability. And we were able to figure out how long you'd actually need to observe to detect a trend given the amount of variability. That was something like 3 times the current observational record. So we got to put a pin in that, come back to it. The thing that I'll spend the rest of my time on is what I'm doing now, or spending most of my time on now, and what I spent most of my time on in my sabbatical when I was in Liverpool, which is building simpler worlds. And it continues on this theme of trying to use an idealized version of a still rather complex model to understand a complex system. And so in this case, the complex system is the global climate system. And the idea here is that we do have comprehensive climate models, but they're still very complicated. And so, the idea is that, like, oh, well, the comprehensive climate model is sort of like a rat model. You want to understand the human, so you use a rat. But the rat, you can only ask certain fundamental questions for the rat model. And so if you really want to understand biology, you look at a fruit fly. And so this is my fruit fly. And what we've done is we've taken, this is work that I'm doing with Kevin Reed and my student, Yue Ma, and some previous challenge group. What we've done is we've taken a real climate model that's used in IPCC type forecasts, and then we've kept all the physics but simplified the geometry. And so we have 2 planets that we call Aqua and Ridge, one that has essentially no land except for these little caps at the poles that we need for the grid. And the ocean is flat at the bottom. And so this gives us a completely zonally symmetric climate. And then we have another climate where all we do is we add a little ridge between the 2 polar that only exist in the ocean. And that dramatically changes the ocean circulation, which then dramatically changes the atmospheric circulation, dramatically changes the climate. And then we can use these 2 different climates to understand what really basic things like, what do gyres do to the climate? And so for one thing, if this is the case where you have no gyres. So you have gyres ocean gyres on bridge and no ocean gyres on aqua. When you have no ocean gyres, your stratification gets very deep. This is temperature. You can see the temperature gets down, temperature looks very non-uniform even at depth. Whereas this is the case where we have gyres and it looks very uniform at depth. That's it's very similar to Earth. And what we find is that when we warm, if we do a warming experiment where we crank up the CO2 in the atmosphere, the two climates respond differently. They initially, track each other relatively close, but depending on how you do it, so this is the case where we quadruple the CO2 immediately. The case with no gyres initially warms more slowly, because the stratification is deep, and so the heat can get into the ocean and get stuck into the deep ocean, so it doesn't warm the surface. Whereas ridge, the heat is sort of trapped near the surface, so it warms more quickly. This is sort of like Earth. But then eventually, this one of the deeper stratification overtakes ridge, and this turns out to be there's a lot of complicated factors involved, but that I won't get into. But so I'll just end there. But well, first before I end, I'll say we're also doing like fancy things like we're simulating tropical cyclones in these models. So each one of these dots is where a tropical cyclone formed. And so the two different climates have very different patterns of cyclogenesis. And then we are also getting into looking at how these different regimes of ocean circulation impact carbon cycle. And so these figures show the carbon flux to the ocean. And so, on aqua, you have a lot of carbon flux going into the equator everywhere and coming out everywhere else. Whereas on ridge, you have this very definite pattern where the carbon this is going out of the ocean, it's going in where it's red. And on ridge, you got very distinct patterns where the carbon coming out is coming out the western boundary. Sorry, going in is going into the western boundary. So it's already been 11 minutes, so I'll stop there.
Question, Christopher. Chris. Yeah, Camazino. So, Christopher, remind me again, what did you say the reason was for the different trajectories when?
So the initial difference is simply that the circulation on aqua is deeper. So when you have gyres, in addition to gyres, you have a thermocline, which sort of makes your upper ocean be about a half a kilometer deep, give or take. Whereas on aqua, you don't. It's all like the Southern Ocean, and so the ocean circulation almost goes to the bottom. And so when you start heating any ocean, most of the heat goes into the upper ocean, the part that's in contact with the atmosphere. And so if you have a much bigger upper ocean, it essentially has a higher heat capacity, so it can absorb a lot more heat. And that sort of stalls the warming of the whole system.
Okay. Yeah, well, take the question while I switch the talks here.
Quick question: have you looked at overturning circulations in aquaplanets, like combining your first two slides? Or
yeah, I mean that's so the contours. So the colors were temperature. The contours there were the overturning.
I see it.
So they are very different. Although, well, there's a lot more. Yeah, there's a lot more that we could do with the overturning circulation that we haven't had a chance.
Great. Thank you, Christopher.